Hi all. I don't see anyone in the call, so let me be on mute. Hi Rohit.
Hello, hello.
Hello. Let me just share my screen. Give me 1 minute. I'm just informed by Sarangs that he'll be joined by some. He will be late by some time, so he'll be joining in another 10 minutes maybe. So in the meanwhile, maybe we can give it a start and then let him join in. So until the last meet we had, which was last week Friday, if I'm not wrong, we started looking into the basics of inferential statistics. So what we started with is that inferential statistics is nothing but a branch of stats where we are simply going to infer the values or the results. We may not be predicting anything exactly, right? This is what we have already formalized. And then we looked into three areas, which I specifically said that these are the three areas in which I would like to divide inferential statistics. It may not be in line with any statistical books or any academic books. It is basis my understanding and my experience that when it comes to inferential statistics, these are the three things which we do. Either we do a basic kind of a hypothesis testing, where hypothesis is nothing but a belief. So that's otherwise known as a null hypothesis or a status quo, which is kind of a blind belief as well, where in majority of the cases, we may not really have any data or any statistical value of my understanding of the situation, but still I am having some kind of an understanding basis, some kind of an intuition. And then there is an alternate of the null hypothesis, which is in itself known as the alternative hypothesis, which is exactly or mathematically the exact opposite of the null hypothesis. And this is a very favorite thing of any statistician, because any statistical test is almost usually performed to find out whether there is any way to reject the null hypothesis. So that's the terminology we learned, that if we are not in agreement with the hypothesis, with the status quo, then we find alternatives. We find, let's say, data to support the conclusion that we can safely reject the null hypothesis, or else we don't say that we accept it. We say we are not able to reject it because we are aesthetically leaving some scope for any other statistician to have a look at the situation, and then that person can, let's say, again try to do some experiments so that they can reject the null hypothesis. Now, other than the statistical testing, we looked into some more statistical tests, or which we are going to, but that's a category we talked about. In which case, there will be more tests involved, which is going to be looking into, let's say, areas related to the variance or the analysis of variance, otherwise known as ANOVA. Then there are other tests as well, chi-square test, goodness of fit test, and so on. And then there is the last part, which is otherwise known as the statistical modeling. Now, this is almost always confused in the industry with respect to machine learning, but I can mathematically assure you that this is nothing related to machine learning, because these modeling techniques are where we simply model the data and try to infer something. We're not trying to predict anything, because what we're trying to predict is a continuous value almost always. And a continuous value can, ideal condition can never be predicted because it is a continuous value. It can take any value, right? It can have a value ranging minus infinity to plus infinity. Then how can you predict a value which is going to be a continuous value? You can only estimate that value, right? You can only estimate what is going to be, let's say, the price of a 2 BHK apartment like the one which I have in the same area where I live, or maybe in the locality where you all live, given that the area has so and so characteristics. So if I'm trying to build a model, then that model is actually a statistical model. It's not a machine learning model. It is nothing that we are trying to learn from the data. Yes, we are learning from the data. We are actually modeling the data statistically to learn from it, but we are really not going to predict anything, because the value of that price of that house, or the rent of that house, whatever we are trying to predict, is going to be in a numerical format. That numerical format can take a value within the range minus infinity to plus infinity. Right. So let's try to continue, and then let's see how it goes. Now, one thing that we did briefly touch, but I would like to again write or draw a diagram, and I would like to reiterate the importance of what we have seen. Maybe this is a very bad kind of a diagram. So let me just draw the x-axis. And what we have looked into is a concept which is known as the central limit theorem. So provided we have a normal distribution of data, then the sampling distribution of the data. Now the one that I've drawn over here is the sampling distribution. So I'm going to call this SD. Okay, so this is the sampling distribution, and how we are taking it is something that we have already seen, right? Earlier, we have already seen how we are taking it. We have 1,000 students. We would like to know if everyone has a bad opinion about teaching skills of particular teacher X. Then I did 50 trials. Each trial had 30 students randomly chosen. And then I gave them a question. You have to rate Mr. X within one value. Out of 5, you take one value out of this range of 5 values, and you give him the answer. So you have to decide whether the person is really good or not. Because I'm taking an average, it's obviously it may have real numbers or whole numbers, as well as it may have fractional numbers. So then if I plot this becomes my sampling distribution. And the usual or the data distribution may actually look something like this. Okay, the data distribution or the probability density function of the data will look something like this. Okay, which is basically something that I have created out of the histogram of the data. So because I've created this out of the histogram of the data, it is clearly the probability density function, right? So now the majority of the cases, or statistically, if it is proven that if I have a good sample and if I am doing a lot of trials, then it is quite clear that I have a very good randomization of my data out of the population. I know that the population has 1,000 students. I may be able to do a survey with 1,000. This number is really not that big, but I've taken a sample of 30, and then I've done at least 50 trials. So I have done what? 30 multiplied by 50, 1,500 combinations. So I have at least sample 1,500 students where there can be repetitions. I accept that they are not unique 1,500 students. How can that be if a college has only 1,000 students? So there will be repeats. Okay, fine. But I've done a lot of trials, and I have taken a good sample amount. If I would like to increase this 30 to, let's say, 300, that would even be better. But then the overlap of each and every trial of the students from the previous trial or the next trial is going to increase. So it's going to depend how I'm going to conduct the experiment. But at the end of the day, if I have a good sample, if I have done a lot of trials, a lot of experiments, then I can say, and then the probability density function follows a normal distribution curve, then I can safely say that the sampling distribution of this probability density function, right, where the sampling distribution is created out of experiments which are extensive, is going to follow a principle which is otherwise known as the central limit theorem. And the central limit theorem says that it is always a normal graph. Okay, so it is always a normal distribution provided number of samples that I have taken, which is n, which should ideally be equal to 30. So if I have cases, if I have trials where my number of samples that I've taken in the trial is going to be more than 30, then I can be sure that basis this condition matches and that I have done good randomization. CLT will be followed by this distribution, where at this point on the x-axis, gives the mean of the sample, otherwise known as the sample mean or the sampling mean, right? When we took the mean over here, if I take a mean over here, if I take the value of mean over here, this is known as the mean of the sample. This is represented by mu, right? This is also represented by mu, but I can also optimize this by actually dividing the number of the samples that I have taken here, because that is actually going to help me uh, decide what is otherwise known as the standard error, right? So mean is always going to be the same, but then I'm not going to calculate the standard deviation, rather I'm going to calculate the standard error. We looked into this in the last class, but I'm trying to repeat this because this is a very important concept and we need to remember that. Just not to get confused, this mu will not be used over here. So let's say we are going to use something x. Let's say if this is x, right, this value is given by letter x, then usually we call this x bar. Okay, this mu is called over here when I am looking into the sample or into the population, but in this case, I'm going to call it x bar, right? And then the standard deviation, which I already know here, it was equal to sigma. I'm not going to call it sigma over here. I'm going to call it sigma divided by root of n, when n is number of samples that I've taken for each and every iteration. If this is the case, then my ideology will be to reduce the standard error. More the number of samples, the numerator will have lesser effect, and hence the overall value of this equation is going to go down, and hence I can clearly say that the standard error is going to decrease, and that is my intention of looking into the central limit theorem or its application, right? Now, basis the central limit theorem, we also looked into something. We also looked into another cornerstone kind of a criteria. Let me take another color here. So if I draw a straight line over here, this is exactly the sampling mean. Then I draw an equal line here and here. Okay. Then I draw another line over here. 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 Okay. Now what I'm going to say is this is my mean. So I'm going to call this x bar, right? This is the distance between x bar on the left hand side is actually -1 standard deviation, right? This distance is -2 standard deviation, and this distance is -3 standard deviation. Okay, what I mean by this is, just to clarify, if I take a pen again, so from this x bar value, which is over here, one standard deviation on the minus side is this much value, two standard deviation is this much value, and three standard deviation is this much value. In the same way, I have one standard deviation this much value, I have two standard deviation on the positive side, which is this, and three is this. Now this, the reason why we are drawing this over here is that this draws the basis of the empirical rule, and the empirical rule clearly says something like this. Let me just use the eraser and try to remove some of the items over here so that I can draw it. So let's just remove all these things. I believe I have also removed the mean line. So I'll draw that line once more. So the mean line is going to be somewhere here. So then the first SD is going to be here, right? So what we can say clearly is that 68% of the data falls over here. So if 68 falls over here, this range is going to be 34. This range is going to be 34. Why? Because I've already told you if it is a normal distribution and I take a distance here D1 and a distance here D2, then it is going to be same, right? So an intercept on the y-axis, and then I take the distance, it must be same, because on this side as well as on this side of the inclination, the shape, the size, the decline, everything is mathematically exactly the same. Then this part, two standard deviation range, this two standard deviation range is going to contain 95% of my variation, right? It is going to contain 95% of my variation, and that's how I'm going to define the second standard deviation rule, right? Now, the third part is this one, where I have included mean plus minus 3 standard deviation, and this defines 99.7% of the data, right? Now, why am I stressing on this is because if you would like to know whether your data really follows central limit theorem, or central limit theorem has to be applied to find out if your data is really normally distributed, you can find out this curve over here, and this curve is what? This is the sampling distribution curve. You can find it out from all your experiments, and then you can figure out using CLT, using the application of CLT, even on top of the sample distribution that we have actually taken here, or the regular probability density function equation as well. You can actually fit the data using this model that we have created, and then you can clearly find out whether uh, mean plus minus one standard deviation has at least 68% of the data in my data set on it. If that number that you are arriving at is near to 68%, you can be 100% or near to 100%, near to 100% sure that yes, you have a normal distribution, right? Then you can also check if x or x bar plus minus 2 standard deviation is going to contain 95% of the data, and then the third condition, which is x bar plus minus 3 standard deviation containing 99.7% of the data. So this is one of the tests that we are doing to find out whether my distribution is a normal distribution or not, and if it is going to follow CLT, because using the central limit theorem, we are going to solve a lot of hypothesis problems. But before we solve hypothesis problems, it is my duty to tell you that when we are going to solve hypothesis problems, we are almost always going to face a very common problem or a very common type of error. And this error can be explained by taking an example, which at this point in time is going to be a very scary kind of an example because of the situation going on outside. But I believe it's a very apt example that we can take. So I'm going to draw a kind of a table. Okay, I'm going to draw a kind of a table. So I have drawn a table over here where on this side, I have two columns. Okay, I'm not going to tell you the names of the columns right now. I'm going to write that down. And then on this side, I have two more columns. Okay, so let me just create the table in a proper way as much as I can. And then we are going to look into a very interesting thing over here. Let me just take the eraser and try to move this. And I'm going to have a table which is something like this. And okay, and let's take the line once more and let's draw it over here. Fine. Now let's say that in front of you, you have a table like this, and I have a lab. I am an owner of a medical lab who does the blood sample and swab sample kind of a testing for all the patients contacted by COVID-19, right? So if I'm doing a test, if I'm doing a test like that, then it is quite obvious that either a person who is doing a test from my lab is going to be a true case, right? It means he has a COVID-19 problem, or that person does not have a COVID-19 problem. So it can either be true or it can either be false, right? Now, what happens? Now there are two options, which the same options I'm going to write on this left-hand side as well. Okay, so I'm going to write these two options on the left-hand side as well, and then I'm going to try to fill up this table and try to find out what is happening over here. Okay. Okay. So if let's say I have somebody who really, okay, who really has a COVID-19 problem, then that person is, let's say, let me change the color, is going to fall in the category of true. That person came to my lab and that person was tested as positive as well. So this is not a bad thing. A person who is really contacted with the COVID-19, I have actually detected him or her properly that the person is actually contacted with COVID-19. Then comes a case when the person does not have any infection and he or she is positively identified by not having an infection, right? So either the person falls into this category or this category, which is really good. It is really good, not in the sense that a person has been contacted with the disease or not. It is good in the sense that the person had a disease and I was able to identify it properly. This is otherwise known as true positives, right? And then there is the second case where the person did not had any disease, and I was successfully able to confirm that the person does not have any disease, and that's why this case is otherwise known as true negative, right? If I have a true positive case or a true negative case, it is not a problem. The problem is on the next two cells which are still empty. Now see what is happening in the next two cells. I am looking at a patient who is actually having, let's say, coronavirus. Coronavirus is inside his body, but then that person is, let's say, asymptomatic. Then if that person is asymptomatic, he does not have any symptoms upfront, maybe before even taking my swab, or maybe there was some problem in the machinery. I actually said that this person does not have COVID-19 infection. So my machinery or my process was not able to detect, right? My process was not able to detect whether the person really has COVID-19 or not. And then there is another dangerous thing happening over here. A person does not have COVID-19 and I'm declaring that the person is actually positive, letting that person go into some kind of a disastrous kind of a situation. Maybe that person will be admitted into hospital, or maybe that person will be, kept in a secluded place and so on. So the person does not have any virus, but I am declaring basis my test that the person has a virus. This case is known as false positive, where the actual answer or the actual outcome I am looking for is false, or actual thing is false, the reality is false, but what has come out of the experiment is positive. Then there is this where it is a false negative. It is actually true, but I have given it a negative value. That is why it is a false negative, right? So this is false positive, this is false negative, this one was true positive, this one was true negative. Now, in any hypothesis test, why I am explaining this is because in this case, my null hypothesis is my tests are brilliant. My null hypothesis is that I have some company, I have some test center. The test center is doing an exemplary job in testing the COVID-19 cases. But that is my status quo. That is my null hypothesis. And the alternate hypothesis is my center is not doing a good job. Right now, when we are doing a null hypothesis, which is in this kind of a situation, then what we do is that anything that falls into the true positive and true negative areas can be safely ignored, because these are not at all errors at all. So barring these values, whatever is left out, okay, whatever is left out, this is also otherwise known as a frequency table. Now, in this frequency table, what we are looking for specifically is the false negative and the false positive case. False positive cases is where actual outcome was false, but I got a true value, right? This is otherwise denoted by the sign alpha, and it is also known as a type 1 error. This is known as a type 1 error, where where uh, just a moment, yes. So this is known as a type 1 error. Why? Because the actual outcome should have been the rejection of the fact that I have coronavirus or not, but the outcome that actually came, ideal outcome, should have been false. The one that actually came is true, right? So that is why this is a type 1 error, or also denoted by the letter alpha. This false negative case is denoted by the letter beta, and this is also known as a type 2 error, right? You just have to remember the names right now. Later on, when we are going to use these, we are going to look into what are the applications of type 1 and type 2 error and what is the significance. Okay, please note that this kind of a hypothesis that we have created and the implications of these true positives and false negatives and so on is also going to come very handy when we are going to do any classification kind of algorithms into machine learning, in which case this table will be otherwise known as a confusion matrix. It is known as a confusion matrix. Very, very bad name. I don't know who has created that name for this table. But as per my view, this should not be called a confusion matrix, because creating a frequency table like this actually helps me to clear a lot of confusions. So that might be one of the reasons why it is called a confusion matrix, but I am not sure. I have not read what is the origin of that name which was given to it. But I do know that we have created such kind of table earlier, right? We have already seen when we looked into an Excel sheet and we tried to find out if there are used cars with AC and used cars with the CD players. So we created frequency tables to find out the marginal probability. So we will as of now stick to the terminology that this is a frequency table. This is simply a table where I'm going to write the numbers, right? I hope you have got the point. These blocks that are going to be here is what where I'm going to write the points, right? So example given, let's say on this box, let me just draw once more this table, and with an example what I can tell you is that, let's say I have tested 100 people. This is true and false, this is true and false. Okay, then what is a true positive? Let's say I have correctly identified 35 people as true positives and correctly identified 35 people as true negative. So 70 is gone out of 100. I have a sample of 100, 70 is gone. So let's say here I have 15 and here I have 15. So these are the numbers that I'm going to collect out of my experiments. And then from the experiments, these frequency table will be created. And then I'm not going to look into this, I'm not going to look into this, because I know 70% of my results are correct, right? So my accuracy in this case, or the significance of this experiment that I have done, is simply 70 out of 100, otherwise known as 70%. So I can blindly say, I can clearly say that 70% of my cases are correct. But then there are cases where I'm interested on, where there are 15 plus 15, 30 cases which are wrong. So 30 out of 100 times I'm wrong, right? So these two values, the ones which I'm calling the type 1 error and one which I'm calling the type 2 error, is actually the measure of how erroneous my experiments are, or how erroneous the setup is. Why I said experiments is because maybe I have not done the sampling in the right way. Maybe I have not collected the data in the right way. So I cannot blindly trust this table, right? So it can well be a problem with the experiment, or it is problem with the null hypothesis, or with the setup, right? So if I'm saying my null hypothesis is that my company is one of the best companies in our city which is actually providing the test, then how come it is going to be a best if there is only a success rate of only 70%? I mean, 70% looks to be a decent number, but if 30 out of 100 people are going to die, or 30 out of 100 people are going to be wrongly classified in this case, this is a huge problem, huge issue. For a country like ours is going to be a big problem, right? So I cannot accept this kind of a failure rate, right? So in this case, I can reject the null hypothesis and I can clearly accept the alternate hypothesis that this company, so and so, is not really doing a good job when it comes to testing the corona patients, right? So this table is really going to come in handy. That is why I wanted to spend some time on this, right? Let's clear all the drawings and let's go back and let's try to see an example. Right, we are going to take an example, because only by means of an example can we really decide what kind of tests we are going to do. And then the hypothesis testing is going to be of two types, which is also what we are going to see using the values of Z. So what we have already seen is, we have seen the central limit theorem plays an important role in inferential statistics. We assume that the sampling distribution of any PDF or probability density function is normal if PDF is normal and CLT can be proved. Okay, now this is vice versa, means if a sampling distribution is normal, then it will always follow central limit theorem. Here CLT refers to central limit theorem, right? Then we looked into the essence of the rule that defined the 68%, 95% and 99.7%, the distribution of the data, which is otherwise known as the empirical rule of inferential statistics, right? This empirical rule is applicable only in case of CLT. So if central limit theorem is applicable on any sampling distribution, then only I can say empirical rule is applicable. And that is the reason why it is so important to get a distribution converted into a normal distribution, that I can directly say CLT is applicable, and hence my empirical rule is also applicable. At a later stage, we'll come to know why it is so important to apply the empirical rule, because this number 95 you see over here is now going to play a very, very important part in our lives. When we are going to do inferential statistics, please note this number is going to prove very, very useful. We're going to define a concept known as confidence interval at a later stage, where this number is going to be really important, right? Then I have looked into a table, which is nothing but a frequency table of any experiment with two possible outcomes, true and false. And this table tells us the accuracy or the scenario of whether to believe the null hypothesis. Whether I'm going to believe the null hypothesis or not will be explained by this table. This table is also sometimes called the confusion matrix, especially in machine learning use cases. Right? Now let's look into an example. If we have time, we will try to solve that example. So let me just create some blank space over here so that I can draw. And then we can see how we can actually apply hypothesis testing. Now we understand what is hypothesis, and now we are going to do a decision making. Now when we are going to do decision making, basis the side that we are going to take. Okay, basis the side, and this is going to be very interesting. When we look at the examples, we will come to know what the application of that side means. So basis the side which we are going to take, our conclusions are either going to be one-tailed or two-tailed. So that is the differentiation, or that is the kind of hypothesis tests then I can have. So if I draw a sampling distribution, I'm sorry, let me just take a curve. So if I am drawing a sampling distribution, which is something like this, and obviously this is going to follow the CLT. So this is the mean. And let's say I have some value which is appearing over here. I have some critical value which is happening over here. I am going to call this value the value that I'm trying to test, or this is my value which I will be very critical of, right? I'm actually commenting on this value or taking this value, and that is the reason why this value is otherwise known as critical value. Later on, when we do the test, we'll see that this is also denoted by the letter Z subscript C. So this is the critical value of Z. Okay, you remember we calculated the Z values earlier, right? We are going to use the same Z value concept, and we are going to apply over here, where this point is going to be my critical value. Why? Because let's say I want to know what is the probability of anything falling in this hashed area. So if I'm going to test for something happening in this hashed area, and I have already seen earlier, this is kind of a repeat for all of you, that the progression is going to be on the right hand side, then this thing is kind of a positivity test, or it is falling on one side or one tail of the diagram, right? So if this is the diagram, this area falls onto one tail, and that is the reason why this kind of a test is known as a one-tailed hypothesis testing, because I'm not looking for areas under the curve at both the tails of this graph. I'm looking at only one of the tails, right? So that is the reason why it is known as a one-tail test. Usually one-tail tests are the most common to find in the market. That's what we are going to start with, because finding an example of a one-tail test is really very, very easy. I found one, and that's exactly what we are going to look into right now. Right? If had it been the case, we were looking for the Z critical values on the other side of the town as well. So we had one Z critical value here and one Z critical value over here. We may have different kind of a nomenclature to define them, but then if we have two values on both sides of the tail, then we are going to call this a two-tailed hypothesis test. Right? Why? Because we are looking at both the tails or both the sides of this sampling distribution here. Right? Let's clear the diagram and let's try to look into an example. So I'm simply going to explain the example. I have a company and I have a product manager in that company. This company of mine, let's say this is in the state of Maharashtra, and I have a line of apparel. So let's say I'm selling them into Flipkart. I started, let's say, from Flipkart, and then I have my own website from where you can buy the apparel. So this is quite famous in the ladies, at least. I have a lot of items which are there into the apparel section. Now, I would like this product manager of mine to introduce a new product line into a new market area, or I would like to launch this apparel kind of thing into some other state. So let's say West Bengal. I'm going to launch this apparel because this is already a hit in Maharashtra. I'm under some kind of an assumption, again a null hypothesis, some kind of without data. I'm coming to a conclusion. This might be a very good idea. Let's go to West Bengal and let's try to launch it. So if I have, let's say, such kind of requirement and I go to my product manager, usually any systematic product manager will say, sir, let's do one thing. Let's go to that new area and let's do a survey, right? Let's do a survey. Let's try to find out what kind of people live over there, because we already know, basis the news that we see on the newspapers all around us, we know how these two states are actually performing. Okay, West Bengal is not really performing at a very good scale, while Maharashtra is doing really, really well when it comes to the monetary value or the kind of taxes that Maharashtra contribute to the entire Indian line. Then we can be quite sure Maharashtra is a correct or a better state when it comes to the comparison between these two states. Although this kind of a comparison is not really good, but we are doing a statistical test, hence a comparison has to be done. So what my product manager does, she goes to, let's say, West Bengal, and she goes to 400 houses. She randomly goes inside 400 houses, knocking on the door, ringing the bell. She says that, sir, I'm from a company. We are doing a random survey, and I would like to know what is the mean income of your house. Right. So what is the kind of income which you have in your house? Even if you are a joint family, that there are more than one person working in your house, I would like to know how many people are working is really irrelevant for me. I would like to know what is the mean income. Right. So let's say that I have, so this is my use case. I don't think we will be able to finish it because we have only 10 minutes left, but let's try to do that. So I have an apparel company and I am already in Maharashtra. Okay, already in Maharashtra, want to launch in West Bengal. Okay, my product manager performs a survey in West Bengal for 400 houses randomly. Okay, this word is very important. Randomly, she has gone to 400 houses. She has noted down the mean household income of each and every house. Okay, okay. Now she has noted down the mean household income, and that comes out to be, I'm sorry, I don't have any rupee symbol on my keyboard, so it comes out to be 30,000 rupees. Right? So on an average, the household income per month of these 400 houses, this is per month, huh? This per month. So per month household income of these 400 houses in West Bengal that she has looked into has a average household income. So this is my mu. Average household income is equal to 30,000. Okay, and then this data has a standard deviation as well. The standard deviation in this data is approximately, let's say rupees 8,000. Right? So with a deviation of plus minus 8,000 value per month, right? This is the data that I have got. Now, what I am simply going to do is I'm just going to reverse engineer the fact that I don't necessarily need to take a sampling distribution in this case anymore, because if I am already sure, based on the central limit theorem and application of a central limit theorem, that my distribution is normal, then I can simply take the probability density function as well. But then before even going into the technicality, what is the question here? The question here is that my product manager does not agree with me. My point was, let's go to West Bengal, let's launch the apparel line. But she is saying that we should not go there. Okay, we should not go there because her null hypothesis is we must launch it in a state where the average income okay, the average income, we must launch in a state where average monthly income must be greater than, not equal to, greater than rupees 29,000, right? But West Bengal is already sufficing this, right? But it has a very large standard deviation. So this is under the assumption that we have less variation or less standard deviation in the data. So this is what she is saying. This is her null hypothesis. She says we should only launch the apparel in a state where the average income is greater than 29,000. So this becomes my null hypothesis. And when we define null hypothesis, we define it by the letter H subscript 0. Here I cannot write a subscript in my keyboard, so that's why I've given it a bracket. In any book, in any textual context, in any exercises, you'll find it as H subscript 0. That is known as the null hypothesis. And my null hypothesis is that I am going to launch this product where mu or average household income is going to be greater than 29,000, right? So this is going to be my null hypothesis, right? So this is going to act as the decision making power for me, right? Now, is that really going to be my null hypothesis in this case? The answer is no, because there is a conflict. So the conflict here is we need to understand what is the null hypothesis actually means. Null hypothesis actually means what is the existing thing, not what I want to have. So this statement that my product manager is saying, this is basis what she's expecting to have, right? So this should ideally have been the alternate hypothesis. The null hypothesis is going to be this. The status quo is the current situation. The null hypothesis is the status quo is we should not launch where mu is less than 29k, right? This is how you word the null hypothesis. Then what? How do we write the alternate hypothesis? We write it as H subscript A. I can't do that in the keyboard, obviously. So H of A is my alternate hypothesis. Alternate hypothesis is what I'm trying to prove. What my product manager is trying to prove is we must launch the product wherever it is more than 29,000. So that is my alternate hypothesis. And that is why in this case, I'm going to write the alternate hypothesis to be greater than 29,000. And then I'm going to see what is the problem with this alternate hypothesis. Right? Alternate hypothesis is here. I'm going to simply where mu is greater than 29k, we should launch where mu is greater than 29k. This is my alternate hypothesis. Now there is a problem. By the definition of hypothesis, we have already seen that the alternate hypothesis has to be an exact opposite of null hypothesis, which means if this is less than 29,000, this should be greater than or equal to. It can't be greater than. It must be greater than and equal to, because that is the exact mathematical opposite of being less than. Right? This absolute value of 29,000 has to be considered, right? The other important point over here is in both of the hypotheses, I have never considered what is the standard deviation. It is my assumption that we must have as less standard deviation as possible, as less variation in the monthly average income of people in that state as much as possible. I have not really put it down in a number. So I'm not trying to control the variance. Okay, this is property number 2. Property number 1 is what? My null hypothesis is exactly the opposite of alternate hypothesis. Alternate and alternative is going to be the same thing, right? The second thing is I am not certain about the specific value of standard deviation. Hence, I will only expect it to be as less as possible. Okay, I'm not going to do any assumptions when it comes to standard deviation. Standard deviation is not a thing to play around with. I do not control the variation. There are multiple factors that can affect the variation of salary. in a state. Just because West Bengal is not doing currently quite well as compared to Maharashtra, that does not mean that people belonging to West Bengal or people who are from that state are actually a bunch of idiots. That is not the point. Because of certain situations, because of certain confounding variables that we have seen earlier, the situation is so that Maharashtra is doing financially better as compared to West Bengal, right? So that is the reason why we can never be in a technical position to challenge the variety of the data. That's why we are not going to challenge the standard deviation of the data. We're not going to do that. Okay, let's not look into it. So this is my test. This is what I'm going to do. This is what I'm going to test. Now, why or how did I tell you that this is a one-tailed test? I started with an example of a one-tailed test. And how is this a one-tailed test? If you simply draw this, you will come to know why is this a one-tailed test. So let's say this is the axis, and then I'm going to draw the distribution here. Okay, let's say the mean that 29th, that 30, the value which is the population mean, in this case that will be 30,000. So the 30,000 value is somewhere here, and then less than or equal to 29,000 is my null hypothesis. But null hypothesis is not what I'm really interested in. I'm actually interested in something else. I'm interested in whatever is greater, right? That is what I am more interested in, because that is what is going to give me the business opportunity. The greater than equal to 29,000 is something what is going to be my actual value. So I'm going to look at something or some value which is on the positive side, only at the positive side. I'm not looking at anything which is on the negative side. That's why this is a one-tailed test. Now, how do I get into this value? How is this a critical value or this Z of C actually calculated? And then how are we going to look into this area under this curve is something that, let's say, we are going to look into the next class, because we don't have more than a minute. I think we can make a stop here. I'll share you all the details. If you have any questions, please do let me know. Let's continue from the next class. Okay. Thank you.
Thank you.
Thank you.
Thanks, Bhamik.